MuseNet is a deep neural network developed by OpenAI that generates musical compositions lasting up to 4 minutes and using up to 10 different instruments. It is capable of merging musical styles from different genres such as country, jazz, and bluegrass, as well as adapting the compositional styles of various artists, from classical figures like Mozart to more modern bands like the Beatles. Interestingly, MuseNet was not programmed with explicit knowledge of musical theory. Instead, it learned to identify and replicate patterns of harmony, rhythm, and style by training on thousands of MIDI files. MIDI files, which essentially instruct how music should be played, served as the dataset from which MuseNet learned to predict the next note in the sequence, deciphering complex musical structures along the way. MuseNet utilizes the same type of unsupervised learning technology as GPT-2, a large-scale transformer model primarily known for text generation. By predicting the next token in a sequence, where token in MuseNet's context is a unit of audio information, the model demonstrates its versatility and adaptability across different types of data. To enable the selection of different composers and instruments, it was crucial for OpenAI to train the MuseNet to recognize and interpret these specific elements. During the testing phase, tokens representing different composers and instruments were prepended to each musical sample. This approach allowed MuseNet to learn how each composer's style and choice of instruments influenced the composition, enabling the model to use this information when predicting subsequent notes. At the generation phase, MuseNet leverages this training by conditioning the creation of music based on the chosen composer in instrumentation tokens. This conditioning ensures that the generated music reflects the specific style and instrumental arrangement selected, thereby producing compositions that are stylistically coherent and personalized. To understand deeper what MuseNet has learned about different musical styles and composers, we can visualize the model's embeddings. Using TSNE, a technique for dimensionality reduction, we can transform these high-dimensional embeddings into a 2D map. This visualization reveals the relationships and similarities between various musical composers and styles as captured by the model, showcasing the cosine similarities among them. MuseNet uses the recompute and optimized kernels of the Sparse transformer to train a 72-layer network with 24 attention heads, offering full attention over a context of 4,096 tokens. This extended context is critical, as it allows the model to remember and integrate long-term structural elements within the musical compositions, quite important in generating coherent and complex musical pieces. In practical terms, this means that MuseNet is specifically designed to handle complex and lengthy musical compositions efficiently. The use of a sparse transformer, characterized by its deep network and numerous attention heads, enables MuseNet to maintain large amounts of musical data in its active memory. This capability allows the model to generate music that preserves the style, thematic elements, and intricate musical structures typical of extended compositions, mimicking how a human composer might develop motifs or themes throughout a symphony. Unlike GPT-2, which utilizes a dense transformer architecture where every token in the sequence computes and uses weights for every other token, the sparse transformer in MuseNet selectively focuses on a subset of tokens. This approach significantly reduces the computational burden associated with the dense attention mechanism of GPT-2, particularly important when dealing with the long sequence lengths seen in music generation. Music generation serves as a compelling application for testing the sparse transformer due to its unique requirements. It represents a middle ground between the fluid token structure of text and the more static nature of images. In music, there is no fixed number of tokens for referencing earlier segments, unlike pixel row in images, making the sparse attention model particularly advantageous. This model allows for flexibility in how the attention is directed, focusing on strategically important tokens that more significantly define the musical structure. Consequently, we can more readily perceive whether the model effectively captures long-term structure, such as maintaining consistent rhythm and thematic integrity, something that is immediately noticeable if disrupted, unlike brief tangents in text generation models. OpenAI curated a diverse set of training data from MuseNet from multiple different sources. This data includes MIDI collections provided by classical archives and BitMIDI, as well as from the Maestro dataset, which is known for its piano recordings. The core of MuseNet's training involves processing sequential data. The model learns by being given a series of musical notes and then predicting the next note in the sequence. To effectively train on MIDI files, OpenAI explored various methods for converting these files into a format that the transformer model can process. Ultimately, they developed an encoding method that integrates each note's pitch, volume, and instrument type into a single token. To further enhance MuseNet's performance, OpenAI implemented a feature known as the inner critic. During training, this mechanism challenges the model to discern between genuine samples from the model training dataset and those generated by the model itself. The effectiveness of each sample, as judged by the inner critic, informs which musical pieces are selected during the generative process. This step ensures that the output not only mimics the training data in style and complexity, but also maintain a high standard of musical quality. While MuseNet is a nifty tool for music generation, it's important to recognize certain limitations that can influence its output. When specifying instruments for MuseNet to use, it's helpful to think of these as strong suggestions rather than strict requirements. MuseNet calculates probabilities across all possible notes and instruments for each note it generates. While the model is designed to favor the instruments you choose, making them more likely to appear, it is not guaranteed to adhere strictly to these choices. There is always a possibility that it might select different instruments based on the musical context it develops. MuseNet also struggles with generating music that involves unusual combinations of styles in instruments, such as pairing Beethoven's composition style with bass and drums. The model performs best when the chosen instruments are closely aligned with those typically used by the composer or style in question. Now, let me show you how MuseNet works. In simple mode, as shown by default on the screen, you hear random uncurated samples that OpenAI has pre-generated. We can choose a composer or style and an optional start of a famous piece, and then start generating. The more fun mode, however, is the advanced mode. This lets us interact with the model directly. In addition to simple mode, we can choose our own beginning sample, but now we can upload our own MIDI file. And then we can also choose the instruments we want the generated sample to have, and customize the number of tokens spent on the generation, which will be the length of what will be generated. Unfortunately, the advanced mode is no longer available. MuseNet is quite ancient in AI terms, as it's from April 2019, and OpenAI has limited support for its web pages. Luckily, I played around with MuseNet back in the day and kept some samples of what it could do. In this example, I let MuseNet extend the popular 2011 internet meme of Nyan Cat in a pop style. the following and also last example, I asked MuseNet to expand on a jazzy tune. It's evident that MuseNet can identify the repeating ostinato, as it improvised a riff over the existing melody quite well.